We're not supposed to, you know, the whole team does.
Right.
Okay, guys, so sorry. Ordinarily, I think I've mentioned that Dr. Horgan has changed the order a little bit of what you guys are covering. Ordinarily, it's like you guys have had 0 NMR by this point, often. So I'm used to sort of doing a pretty elaborate NMR spiel. I guess I will try to hurry it up a bit, just gloss over and we'll see where we're at. Right? Yeah, so this is our last meeting. Heating. Nucs. Week 2. And sort of the main goal of today, before I forget too, the facilities lab manager looked at the IR and thinks it's behaving itself. So did everybody keep their diphenylacetylene from last week? Yeah. All right, so let's give it another try. Aaron, maybe you can borrow some from somebody. We'll see.
And if it doesn't work, are you going to send us
I'll figure it out at that point, yeah. Okay, so the main goal today is figuring out our ratio of our bromide versus our boron. Okay? And you know, each of you have 2 of them that you need to do. You need to do either your 1-butanol reaction that you did or your 2-butanol reaction that you did. Well, and you also need to do your T-butanol that you did, otherwise known as 2-methyl 2-propanol. And the 1-butanol or 2-butanol reactions are going to be analyzed by NMR, okay? And then the T-butanol by GC MS. Okay? All right. So let's see. All right, proton NMR. Okay, so what is sort of the purpose of proton NMR? Proton NMR gives you a signal for each type of proton on your molecule. Okay. Now, type, I'm leaving type purposefully a little bit vague. So in a second here, we'll talk about, well, what the heck do we mean by type? Gives signal. Which type? Proton in the sample. Okay. All right. Well, so if we're looking at type, quote-unquote type of proton, we can use the quote-unquote last quotes today, little man technique.
Oh, I remember this.
I actually, I guess I should have 2 different ones. It's a little bit different than the little man technique that I talked about for figuring out chirality, where if you're, yeah, maybe this should be the little woman technique. And the basic idea is, well, first, one quick caveat. For the time being, you should assume if the protons, if the H's are on the same carbon, they're the same type. Okay? And the majority of the time, that's true. I will put a little asterisk on that idea. For the purposes of our discussion and this worksheet and everything like that, if they're on the same carbon, they're the same type. But I want you to put a little asterisk on your paper and in your brain that there are situations where if you have a CH2, those H's can actually be different on a CH2. On a CH2, they're basically never different. Okay? But there are certain circumstances where a CH2 can be different. But for the purposes of our discussion today, for the most basic introductory discussion of NMR, if they're on the same carbon, they're the same type of proton. All right? Okay. Okay, so let's look at this technique with an example. All right. How many types All right, so what do you think on that molecule? How many, if all the H's on the same carbon are the same, how many different types of protons do we have? That, maybe I should, before you answer, sorry, maybe I should tell you the little man technique in this context. Little man technique in this context is, let's say you think, oh, I think that type is the same as that type or something like that. Okay, we'll test it by shrinking yourself down and going on to that H and looking down the molecule. It is a lot like the chirality one. I look this way, I see a CH3, I look that way, I see CH2, 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 blah, blah, blah. Now come over to the other one that you think is the same as that type. Look around you, do you see the same stuff when you look on both your sides? Okay? If you see the same stuff, the exact same stuff, then it's the same type of proton. Does that make sense? Okay, with that in mind, how many types of protons do we have? 3, yeah, great. Great, that's evidence you guys have had some NMR, I think. Yeah, so these guys are the same. Those guys are the same, right? And then he's all on his own. In NMR, we very frequently will find our types of protons, and then we'll give them a label. So, good thing to get used to that idea. A, B, C, and that's also B, and that's also A. Okay, wonderful. All right. All right, so for each type of proton, you're going to get a signal. Every once in a while, by the way, the signals, and it can be kind of a bummer. Just because they're different types doesn't mean they don't fall right on top of each other, and then they kind of make a jumbled mess a little bit. All right. But sort of the main purpose of NMR in general is a very general statement, and then I'll make more specific statements about the purpose of NMR. In general, proton NMR tells about your carbon framework. Right? Organic compounds are these frameworks of carbons, right? These lattices of carbons. And it might be decorated with an oxygen or nitrogen or halogen someplace, and so forth and so on. Okay? And then there's a lot of H's. All right? IR doesn't doesn't tell you a whole lot about how things are assembled. Melting point doesn't tell you that. TLC doesn't tell you that unless you have a sample of the exact same compound. Okay? So how are those carbons all connected? That's a pretty subtle thing to get at. And remember, there's no microscope where you can look at an individual molecule. Okay? So you need sort of indirect evidence as to what your carbon framework looks like. Okay? Now, there are three more specific types of information that NMR gives you, and collectively they answer that question for you. Okay? Or go a long way in answering it. All right. Okay, so three more specific types. Info. They tell you about framework. Okay. All right. So what are they? Well, the first one is shift. That is where, so like for instance, for this guy, you know you expect to have three different signals, okay? Where are those signals going to come on your spectrum, on your proton NMR spectrum? Okay? Where on the spectrum? All right. There's sort of an unusual scale, okay, that's part of NMR, which you guys are probably familiar with because you're a little bit ahead of the curve on NMR, right? It's the parts per million scale. And essentially this wacky scale is because our instrument could have subtle differences. It's a subtly different environment, like a little bit stronger field, a little bit weaker field, compared to one over in UH, compared to one in China, but we don't want there to be different spectras because of differences in the field strength of our different NMRs, right? If it's the same compound, we want all those different NMRs to yield the same spectrum. So we use a parts per million, scale. Okay, that wasn't the best explanation of what we do, but nonetheless. Let's talk about where different signals come. What is this? So if this is 0 ppm, okay, 1, 2, 3, 4, 5, 6. 7, 8, 9, okay, what is this part? What is this area referred to versus down there? I just gave you a hint.
The downshift.
Close. This is upfield and that's downfield. This is up. And this is all right. Okay, so I'm just going to put some. Where you are on this spectrum has to do with what type of things are connected near you. Okay. As a really sort of oversimplification, but pretty good one. The more electronegative, or another term for that we could use, is electron withdrawing. The more electron withdrawing or electronegative the stuff around us, okay, having those things around us strips us of electron density. We have less electron density on us, okay? The more we are in that environment, the farther downfield we are. When we're not around stuff that's super electronegative or super electron withdrawing, we tend to be more upfield. Okay? A real sort of simplistic way of thinking about it is you feel the external magnet stronger. Okay? You've been stripped of your electron density, which was shielding you from the external magnet, which means when the 90-degree angle is released, you will resonate back at a higher frequency, okay? Because you feel that magnet more. All right. If you, let me switch the numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If you are a CH3, okay, and R is just carbon framework. It's not something electronegative. Okay, just regular carbon framework. All right, so this is a CH3 that's not in a very electronegative or electron withdrawing type of environment around it. Then it's going to be right just before 1. Okay. All right. In the 1 to 2 area, this is your CH2s, okay, or your CHs. All right. Your CHs tend to be a little bit more downfield, all of the things being the same than your CH2s, but not huge differences there. Okay. Okay. Now, in the 2 to 3 range is stuff like let's say you have a carbonyl, okay, and you have an H that is on an adjacent carbon to a carbonyl. Anybody know what type of carbon that's called when it's adjacent to a carbonyl? That Dr. Orman's probably mentioned it, but it's not sticking. It's called an alpha carbon. Okay, you have an alpha carbon, and then the H's on an alpha carbon are alpha H's, alpha protein. If you have a CH and it is attached to a nitrogen, okay, tends to be in this area. You have does anybody know what position this is called? Where it's a carbon that's attached to an aromatic ring? Okay. What position that's called?
Beta.
What's that?
Beta.
Nope. A beta would be over here, one more carbon out. That's called benzylic. Okay. And then also in this area, running out of room, grounded area. Is that H? Anybody know that one? Allylic. Okay. When you start to learn about carbocations, these are the exceptions to primary. Those are willing to form primary carbocations. So, fun fact. Okay. is a proton on a carbon, and that carbon is attached to a halogen. Okay? And let's put a little asterisk on that guy. All right. And what does that asterisk mean? That asterisk means that there is a certain trend that holds true. I should put the asterisk on the X, that holds true as we go from fluoride to chloride to bromide to iodide. Okay? What do you think? Where, in terms of this range, 3 to 5, where would you expect if X was fluoride? Yeah, exactly. Why? Okay.
Because fluorine is more electronegative. So
Exactly.
it shields the
Yeah. Perfect.
proton.
Perfect. Electronegativity increases as you go up the periodic chart. Fluorine is actually the most electronegative atom on the periodic chart. So the more electronegative, the farther downfield. Asterisk number 2, that's most of the time. Okay? Most of the time, absolutely true. All right? We are going to see an exception to that. That's important that you know that. Okay. And then, just to complete this out, even though it's not that pertinent to us right now, today, if you are an H on a carbon, and that carbon is attached to an oxygen, then you tend to be between 3 and 4. 5 to 7. What comes in the 5 to 7 range, guys? Not too much else in that area. What's that?
Benzene rings.
Very close, actually.
Are those at like 6?
Benzene rings, aromatic protons tend to be a little bit farther down. They're H's that are on an alkene, on a double bond. Okay. And then aromatic tend to be in this range. And then you got some aldehydes down by 9 and 10, and carboxylic acids down by 12-ish. All right. And not terribly helpful. That is OH NH. Those aren't all that useful sometimes in NMR. Sometimes they are. So where your signal comes gives you already some information about framework. Yeah? Does that make sense? Oh. All right, so that's the first thing. Okay, the next bit of information that you get, a class of information that you get, is multiplicity. So multiplicity is the appearance of sigma. Okay? What it looks like. spikes. Okay. All right. So, I actually left up my molecule. I've got, okay, this type of proton, all right, is a distinct type of proton. I got some idea of where it is going to be on the scale. And now I want to know what that signal is going to look like. What determines what that signal is going to look like? Does anybody remember?
Is it the singlet, doublet?
Exactly. Yeah, singlet, doublet. So those are the varieties that it can be. It can be a singlet, it can be a doublet, it can be a triplet. But what determines whether it's a singlet, a doublet, or a triplet?
Neighbors.
Number of neighbors, yeah. What's the rule we follow? Once we've counted up all the neighbors that this guy has, what's the rule?
N plus 1.
N plus 1. Yeah, exactly. Okay. So your appearance, I'm a hydrogen, I'm a carbon. My appearance, what signal I'm going to look like, is actually determined by the number of protons on neighboring carbons. It can actually be other atoms too. If that was a nitrogen and he had an H, that's a neighbor as well. But most of the time we're talking about neighboring carbons. Okay, so multiplicity of this signal, okay, dot, 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 depends on number of H's on neighboring carbons and other atoms. Okay. All right, and so, and it follows n plus 1. So what is that? Well, let's say there's n neighbors, okay? There we go. Yeah. Okay, so if you have no neighbors on neighboring carbons, what does your signal look like? Singlet, yeah. If it's one neighbor, doublet. Two neighbors, triplet. There's different heights to the spikes, okay? And I'll just leave that to your lecture class to go over why that's the case. Quartet. Quintet. Sextet, and heptet. Okay. So you can see how this is giving you framework information, right? Now you know how many neighbors. Now you can go, oh, well, this is what I think the molecule looks like. I'll assemble it this way. Oh, no. Now that's that signal. That's really downfield because it's attached to an oxygen, so I know it's that one. But he's got no neighbors. And this signal's a doublet, so I know he's got one neighbor. Okay, so it can help you try to assemble an unknown carbon framework or confirm a carbon framework. You think you know what it looks like, so you better find the signals then. Okay? NMR is pretty good. If I like to say NMR don't lie. Okay? If you've got a signal, all right, and it's not junk. Sometimes we get junk in there. They're all a little impurity and stuff. size compared to the other signals, okay, you better be able to account for it. There better be a reason